Happy December 13th! Today I want to talk about one of the most fascinating discoveries of particle physics, and that is the discovery of the top quark. Now the background to the discovery really comes from the observation that there were three generations of matter. Now physicists had known this for quite a long time. It was known that they needed at least 3 generations to give us the CP violation we had talked about earlier, and they'd already discovered the bottom quark. And then they were looking for the top quark. Now, on the way to discovering the bottom quark, they actually made a mistake. They discovered what was called the Oops Leon particle. It was just a statistical bump. As they gathered more data, that bump went away, but a new bump, which is called the upsilon, remained. And the upsilon gave rise to the discovery of a bound state of B quarks. So they were in a situation in the 1970s where they discovered the third generation of matter. They had the tau lepton, which we discussed previously. They had the bottom quark, and now they were looking for the top quark to fill the gap. It took about 2 decades to find it, a phenomenally long amount of time. And the reason for this was because the mass of the top quark was so huge. It's 175 gigaelectron volts, give or take. And this is the heaviest known fundamental particle out there. Now, some people are starting to worry a bit as we didn't discover it. We were getting to higher and higher energies. We had discovered the W, we had discovered the Z, and the only things left really were, well, there was the tau neutrino, there was the top quark, and there was the Higgs boson. And pretty much everything else had been found. Eventually, the tau neutrino was found in reactor detectors, and the only things left are the Higgs boson and the top quark. If we didn't find the top quark, we were in trouble, because then the whole model of fermions would fall apart. We wouldn't claim to understand the quarks and the leptons if we couldn't find the final member of the third generation of fermions. Eventually it was found at Tevatron, in both CDF and D0, and its mass came out very, very high, somewhat higher than some people had expected, and we had indirect limits on the mass. We took a look at the B sub S meson mixing rate, and that turned out to be very high. And when that rate is very high, that means the top quark mass must be very high. And so there are indications that it would be extremely heavy. And so what happened was they discovered that it was consistent with what they'd seen in the B sub S and B sub D mixing, and it also gave us some hints on the mass of the Higgs boson as well. Once you know the mass of the top quark and the mass of the W, you can combine those to place limits on the mass of the Higgs boson. And that is what happened. We have limits on the mass of the Higgs boson. Now we know what mass must be, and this is all consistent within the standard model. Now, when you produce the top quark, you generally have to produce a TT bar pair, top, anti-top, and then the top decays almost instantly to a W and a B. And the reason for this is because it's heavier than the W and B combined, so it decays almost instantly. The W can be detected as a lepton and a neutrino, and then you need to find B quark. That usually manifests as a B jet. So you end up with a situation where you have an event with 2 Ws, which can go to leptons, and 2 B quarks, and a load of other stuff. It's a very messy event to actually untangle, and this was done at Tevatron. It's a very impressive result, and it sort of laid the way for the next decade or so of high energy research. They knew where the top quark was, they knew how to measure its properties, and that also constrained the Higgs mass. So it was a fantastic discovery, and it completed our view of the fermions. Okay, I'll see you tomorrow.